In this video, I will talk about the process that we can use to find expressions for the magnetic field created by wires that are not short, like long wires or circular loops, and so on. I did show you that if you use Biot-Savart's law for a single moving charge and you multiply it with the number of charges that you have flowing in your wire, in your short wire, you get this. And this is Biot-Savart's law really for a short wire. There is no new physics. We just use Biot-Savart's law for a single charge and the superposition principle multiplied with the number of charges to get this. And you can tell that the pattern, the form of this expression and the one for a single charge is really the same. You have the constant, the distance squared, and the cross product. Here, the difference is that here you have a lot of charges, not just Q1. Now the difference is this is valid if you have a short piece of wire. But now I do not have a short piece of wire. I have a straight wire that is not short. And I do want to find what is the magnetic field here. So this will be the observation location. And that means I want to find the magnetic field at that point. And this is the object. This is the wire that creates the magnetic field here. Now, as I said, now I will talk about the process. Okay, it's a thought process that we can use, and we do use very often to find magnetic fields from those current distributions. Okay, let me make a note. This will be an example of a current distribution. Another example is if you take this and you fold it, you make a circular loop. That's another example of a current distribution. All right, so for the process, what I'm gonna do, I can choose, I can say the origin is here, this is X, and that's Y. Okay. This is what I'm going to do. I'm going to choose an arbitrary piece from this wire. Okay, this is it. This is my arbitrary piece. What I will do, since this is now a short wire, I can find the magnetic field here created by this short piece of wire using Biot-Savart's law for short wires. So I can do it. B, let's say from that piece is equal to the constant I1 delta L1 cross R hat from 1 to 2. Okay, I'm using this, and let's call this piece 1 since I'm using from 1 to 2, and 2 is the observation location. Now, or let me make a change to my notation. I'm not gonna use 2. I'm gonna stick with observation location so that I can use the numbers on the wire. That's the observation location. All right. Now, excuse me. I just found the magnetic field from this short piece of the long wire at the observation location. Why not do the same thing for the next small piece? For another small piece of wire that I call number 2. I can do that. So from 2 to the observation location will be again the constant. The same current, now it will be delta L2 cross R hat from 2 to the observation location. And I can find it. I'm not using any numbers. I'm focusing on the process here because I want to give you an idea how the equations that I will show you next, how these are derived. There is a meaningful process behind those equations, and it's important for my students to understand what is that process. Now, I found the magnetic field that 1 creates at the observation location, the magnetic field that 2 creates at the observation location. I can keep cutting this current carrying wire into pieces, 3, 4, and so on. Okay, so you have to keep doing that, and all of them, not just there, but also this way. And then when I have all of those magnetic fields, what I can do, I can say, well, since I found all of those magnetic fields, then the net magnetic field at the observation location will simply be the sum of all of those. B2 at the observation plus B3 at the observation, and so on. You just need to add the rest. So this will give me the net magnetic field at the observation location from the whole thing. Okay, I used the expression for a short piece, and knowing that the magnetic field here from short piece number 2 is not affected by the magnetic field here due to the short piece number 1 superposition principle, I can just add them together. Add all of this together, you will get the net magnetic field. Now, this is a process that you can use not just for a straight wire, but for a circular loop, for a triangular loop, for whatever you have, you can use this process. Now, using this process will give us, okay, I will talk about it, but I will not show you any equations. So using this process will allow us to find the magnetic field from a long wire, will allow us to find an expression for the magnetic field from a circular loop, will allow us to find an equation for the magnetic field from a solenoid. Okay, I will be showing you in other videos what those equations are and how to use them. But I do want you to understand that there is a meaningful process that we use to obtain those equations. And everything starts, if you remember, even before this, I was using Biot-Savart's law for a single moving charge. Everything started from there. Once you have the magnetic field from a single charge, you can find the magnetic field of a short piece of wire. And once you have this, then you can break your wires into small pieces and add up all the contributions, and then you will be able to obtain, for those specific cases, wire, loop, solenoid, you can obtain equations. So this is the process that we always use. I do want to mention one more thing. When you do this summation, it is, of course, and you can think about this, the smaller those pieces are, the better your calculation will be. Okay, because the shorter these are, the more accurate this becomes. The smaller the approximation is that you're making. So when we do in theory, when we work with theory, we make these small pieces infinitely small, and we end up using integrals. we convert the sums into integrals because those allow us to have infinitely small pieces. Now, it is possible that if you start working with more complicated cases of more complicated current distributions, it is possible that no analytical expression exists for what you want to do. Okay, if you're working on something new or something that you simply cannot find an equation for it, then what you do in those cases, you have to use a computer to do these calculations. And what the computer will do for you, it will break your wire into small pieces, and it will find the magnetic field from each one of them and then add them together. But these are going to be time-consuming calculations, and those will need to be done by a computer. There is no need for a human to spend time on doing that kind of work, and it's not typically done. We do use computers to do those calculations.